Well, the tank of volume is given with the temperature and pressure and contains saturated air. So let's list the information that is given to us first. As the rigid tank, volume is 10 meter cube. Temperature, which is the dry bulb temperature, and the total pressure is 101 kPa, standard atmospheric pressure. And also is given that saturated air, which means what? The relative humidity is 100%. And we're supposed to find specific humidity. So let's list a few things we want to find. Let's say we want to find specific humidity, pressure of water vapor, pressure of dry air, mass of dry air, mass of water vapor, and specific volume. So all these quantities we have already, all these properties you already know what they are. Let's see how we find these quantities manually and verify using appropriate TestCalc. And when you find them manually, let's do both ways, using formulas and using the psychrometric chart. Okay, first thing first. The total pressure is given to us, so we know total pressure is PV plus PA. And what is PV? PV is phi times PV max. And PV max is also called PG, the G point in your PC model, or P set at the given temperature. In this case, phi is given to us as 1 or 100%, and P set at 25 degrees Celsius. We can quickly go and check that out. So we go to property tables, and to find the saturation pressure from a given temperature, we go to the temperature saturation table. At 25 it is 3.169 or 3.2 kPa. So we found PV. So one thing is done, and therefore PA we can find from 101 is the total pressure minus 3.2 kPa. So therefore PA can be found 101 minus 3.2, which is 97.8 kPa. So we already found two different quantities. Let's go ahead and calculate omega. And recall that omega, which is the humidity ratio or specific humidity, is the definition is mass of vapor over mass of air, which is given by the following formula. So if you know the vapor pressure and total pressure, we can obtain omega from this formula. We can easily calculate that. Therefore, PV we just showed is 3.2, 10 minus 3.2, and that turns out to be approximately 0.02. And the unit will be what? Kg of vapor, kg of dry air, right? Or most of the time, the vapor is so small, it is multiplied by 1000 and it's written gram of vapor per kg of dry air. That's sometimes the unit used in the psychrometric chart. So we calculated omega, we calculated PA and PV. Let's go and calculate the mass of dry air. So to calculate mass of dry air, we can use PV equals pressure of air, volume, MARAT. So when you use this formula, we can obtain the mass of dry air as pressure of dry air times volume by RA times temperature. substituting the values, which are, we already figured out the pressure of dry air in the previous section for 97 point, this is 9, oops, 97.8, 10 meter cube, 0.287 is RA, and temperature is 25 degrees Celsius, which is 273 plus 25 Kelvin, and that turns out to be about 11.44 kg. And now that we know omega, omega is 0.02 and ma, therefore mass of vapor is simply omega times mass of air, so it's 0.02 times 11.44, and that turns out to be approximately 0.23 kg. So the tank is holding 11.44 kg of dry air and 0.23 kg of water vapor, and the air is completely saturated at that point. So the specific volume is quite simple because we know the volume of the tank. Recall that specific volume is defined as volume per unit mass of dry air, meter cube per kg of dry air. Volume is known, given in this problem, 10 meter cube, and mass of dry air we just calculated to be 11.44, and that gives us specific volume to be about 0.874 meter cube per kg of dry air. So let's see different ways of solving the problem. So again, we would like to find out all these variables. We would like to know what is omega, what is PV, PA, MV, MA, etc. using the psychrometric chart. So let's go and try to calculate these quantities using the psychrometric chart. So we will start property tables, and psychrometric chart is table F. We open the chart and let's see if we can locate the state. So as you recall, this is our temperature axis. This is our temperature axis here, dry bulb temperature. As you can see, it goes from minus 25 to plus 55 degrees Celsius. And these are our PV omega axis. I know it looks complicated, but let's see what is given in this problem. We know the temperature is 25, and we also know it's saturated. So remember the saturated line, phi equals 100% humidity. See, these are the humidity values, 90% line. This is the 100% line. And 25 degree, actually 25 is also written here. So this is exactly our state. So this is the state. So we located the state on 100% humidity line and dry bulb temperature. Now that we know the state, we can read off a lot of variables here. First is, this is the relative humidity, the specific humidity, I'm sorry, given in moisture per kg, gram per kg, gram of water vapor. So look, it's 20 here, 22 here, so about 20 point, I would say the value we get is about, if you have to just 20.2. So we find specific, so we find this state to be, from here we can pick up the value to be approximately what we got, 0.02. The vapor pressure is given in millimeter of mercury. Of course, you can convert that if you want into kPa using a converter. And notice the specific volume lines are these lines, and there's a line passing here, there's another line passing here, that value is 0.88 here, 0.86 here, so this must be 0.87. So pretty close to 0.87, I'll say. So I'll just pick up specific volume to be 0.87. So we found omega from here, specific volume from here, from this line of constant specific volume. And knowing the vapor pressure, one can calculate the dry air pressure. Let me clear this screen and go back here, and you will see the specific volume is close to what we got manually. Let's go and verify the solution now using a TestCalc. For that, we launch a system state. The moist air model is right here, and if we go to the tab that says TestCalc, that will launch the moist air model. This is a little complicated TestCalc because in addition to the regular thermodynamic properties, it has additional properties like vapor pressure, dry air pressure, maximum vapor pressure called PG, relative humidity omega, etc. And there are properties that we haven't even covered yet. Also, complicating additional properties, the same TestCalc can be used for moist air as well as pure water or PC fluids such as R134A, etc. So if we choose H2O, notice that all these additional properties of moist air are disabled and we get back into regular properties. So the design gets complicated because these quantities such as specific volume can be used for moist air as well as for say H2O. When used for H2O, the unit is obviously meter cube of H2O per kg, meter cube per kg, whereas for moist air, the unit really is volume per unit mass of dry air. Even though it's not written here, if you put the pointer over the variable in the message panel below, you will find this clarification. So in other words, whenever we select moist air, we got to understand the mass, which is given here is mass of dry air. So really is so many kg of dry air, which is broken up in this case into vapor mass. So the vapor mass and dry mass together makes the total mass. So likewise, every unit, say for instance enthalpy, which has a unit of kilojoules per kg for steam, is really kilojoules per kg of dry air. So that one thing is implied in this TestCalc. So anyways, while solving problem, it's just like any other TestCalc. So in this problem, we know the total pressure, which is given by P. We also know the temperature, 25 degrees Celsius. We know the volume of the tank, 10 meter cube. And relative humidity is given as the saturated air means 100%. And that gives us all the variables of all the properties of the moist air. Obviously, relative humidity being 100%, you can see that mass of vapor and the maximum mass of vapor, which is mg. Mg is basically our mv max. They are equal. Omega is found here, one of the variables we are after. Specific volume is found here, which is meter cube per kg of dry air is the correct unit. The vapor pressure is given here and the dry air pressure is given here. So these two should sum up to the total pressure 100 kPa. Or in this case, it might be 101 kPa. So we could put that. And let me recalculate this for 101 kPa. Okay, so we got the modified answers now. Also, notice that if we do a psychrometric plot, the state will be shown, saturated state. And if you want, you can you notice that the saturated state 1 has been found, just like you saw in a psychrometric chart. And you can draw various lines, such as line of constant, of course, constant omega line will be a horizontal line, and a constant temperature will be a vertical line, and constant relative humidity is already known here, which is this one, really constant relative humidity 100% right now, so it matches with the saturation line. So, in short, this test calc will be used for solving more complicated problem when you have to change between moist air and H2O to find different kind of complicated psychrometric problem, to solve different kind of problems. But as far as finding moist air state is concerned, as long as you enter the given information, this will spit out all the other variables of the state.